Hello, welcome to week 1 lecture 5. In this lecture we will be having a problem solving session. We will look at some problems related to affine ciphers and some problems related to Shannon's theory of perfect secrecy. Now affine ciphers. Now let us recall once what we mean by an affine cipher. In the case of affine cipher, P equal to C, both are equal to Z sub 26 and the key space K is an ordered pair of elements of Z sub 26 such that GCD of A and 26 is 1 and B can be any element in Z sub 26. The encryption function E sub A comma B when it operates over X is AX plus B mod 26 and the decryption function D A comma B operated over Y, which is the ciphertext, is A inverse Y minus B mod 26. Now we have already studied these things. Now we have a question here. Suppose somebody gives us an encrypted character. Let us say this ciphertext is 17. So suppose he gives us y equal to 17 and asks us to find out the corresponding x. How will we do that? Now he has also to give me the key. So suppose the key is K equal to 9, 12. So we know the decryption rule is D sub A B Y is A inverse Y minus B. Therefore the decryption of 17 will be x, which is equal to D of 9 comma 12, and here instead of y I will put 17. This is equal to A inverse, that is 9 inverse, and then y, which is equal to 17, and B is 12. So I will get this. This is what I have written over here. Here I have to replace y by 17. Now I have two options. I can compute the general decryption rule as I have done before and as it is written in this slide, but I can do something else which I am showing here. So once we know that the encrypted message is 17, therefore I can put 17 over here instead of y, and therefore I have got 9 inverse 17 minus 12, and this is of course has to be reduced modulo 26, and here I have got 9 inverse into 17 minus 12 is 5 mod 26. Now the question is, what is 9 inverse? When we are actually doing the problems, we can use our observations. So I want 9 inverse mod 26. Now that means I want a number which when multiplied to 9 and reduced mod 26 gives me 1. What is that number? If we see from 2 nines are 18 is of course not 1 modulo 26, but we hit the correct answer if we check with 3, because we see that, let me write this note over here, 3 into 9 minus 1 into 26 gives me 27 minus 26, which is equal to 1. Therefore, 3 into 9 gives me, is congruent to 1 mod 26. Therefore, I can write that 9 inverse is equal to 3, or in other words I can write that 3 equal to 9 inverse mod 26. Therefore, here I will replace 9 inverse by 3 into 5 mod 26, which is equal to 15 mod 26. Thus, I know that if my key is 912 and if my ciphertext is 17, then the plain text is 15. Now, we can have many other problems like this, and you will get some problems like this in the assignment. We can as well try to cross check our result by going the other way around, just to check whether really everything is all right. We can start from x here and use the encryption rule, which is given over here, by putting the appropriate values of a and b, and then we can check whether we are indeed getting 17 if we start from 15 as the plain text. So, now let us try this one. Here I know that a is 9 and b is 12. Therefore, I write e sub 912 into x, which by definition is 9 into x plus 12 mod 26. Now, I know I am putting x equal to 15. So, e 9 comma 12 into 15 gives me 9 into 15 plus 12 mod 26, and this is 135 plus 12 mod 26. This is equal to 147 mod 26, which is 17. Well, this is 17, because if you divide 147 by 26, let us see this division over here as a note here. So, suppose I take 26, I divide 26 by 147. So, 26 into 5 is 130. So, if you put 5, this is 130, 26 into 5 is 130. If we subtract 130 from 147, we get 17, which is the remainder, and therefore, I am writing it over here. Thus, we see that our calculations are correct. We started with 17, y equal to 17, the key was 912, and we computed the inverse transform of the affine cipher, which is the decryption of affine cipher, and we got 15. Now, we start from 15, use the key and use the function for the affine cipher, and we find that we are getting 17. So, everything was all right. So, we have got our answer. Now, there is just one note over here, that when we are defining affine ciphers, we really do not have to stick to the modulus 26. We can define affine ciphers over other moduli, let us say 15. So, we can take m equal to 15 and consider affine ciphers over z sub 15. So, let us have a look how it will look like. So, we will just change this z by z sub 26 to z sub 15. So, these are numbers from 1 to 0, 1 to up to 14, and the key space will change to something like this. It will be A B in Z15 cross Z15 and GCD of A and 15 is 1. Now, let us quickly check one key and how to find out encryption and decryption functions. So, here in this case k equal to 2 comma 9 is a key. Please note that this is not a key if we take z sub 26, because 2 is not co-prime to 26, but in this case 2 is co-prime to 15 and therefore it is a key. And suppose we have to find 2 inverse mod 15, that is also not difficult to see. 2 inverse mod 15 is going to be 8. The reason is that 8 into 2 minus 15 gives me 16 minus 15 equal to 1, and therefore 8 into 2 is congruent to 1 mod 15. Thus, the encryption function will be like this: E sub 2 comma 9 of x is going to be twice x plus 9 mod 15, and the decryption function d 2 comma 9 of y is going to be 2 inverse into y minus 9 mod 15, and I can safely put 8 instead of 2, and y minus 9 well, I can put instead of minus 9 I can always put plus of 6, because this is because minus 9 is congruent to 6 mod 15, and I have got this mod 15, and therefore this is 8y plus 48 mod 15. I can reduce it further, it is 8y plus 3 mod 15. So, this is the decryption function, and now I can plug in any x and y to find out the encryption or decryption of particular values between 0 to 14. We will also see many problems like this in our assignments. Next, we come to a problem related to perfect secrecy and the computations of different probabilities of plain text and ciphertext and keys. Now, here we have a cipher using a Latin square. A Latin square is a 2-dimensional array of numbers such that no number is repeated in a row or a column. So, here we have a Latin square L of order 3, where we have got 3 numbers and a 3 by 3 array, and please note that there is no repetition either in the rows or in the columns. So, I have got 1 2 3, 3 1 2, 2 3 1, and I have got 1 3 2, 2 1 3, 3 2 1. Now, we can use a Latin square to construct a crypto system, and this crypto system is one such crypto system. Now, we take the PCK to be 1, 2 and 3. and the encryption is defined in this way. We choose a key I which is a number between 1 and 3, we write E sub I and j is my plain text, it is again a number between 1 and 3 and Eij is the element Lij, Lij is the element of the ith row and jth column of the Latin square L, and that number is the ciphertext. Now, suppose that every key is used with equal probability, that is probability that capital K equal to 1 is equal to probability that capital K is equal to 2 is equal to probability that capital K is equal to 3 equal to 1/3. So, keys are equiprobable. Now, we will go to show that this cipher system achieves perfect secrecy here. In order to do that, we have to show that the conditional probability of x, that is the plain text given any value of y, is same as the probability of x. So, we will show that. The first step is to check the probabilities of yi. So, here I have chosen any I between 1 to 3. So, we have probability of yi. Now, let me write down one step in between whatever is shown in the slide. So, this is equal to probability of yi and k1 k equal to 1 plus probability of y equal to I k equal to 2 plus probability of y equal to I comma k equal to 3, because these are the possible keys. So, we have to see that what is the probability that y equal to I occurs with k equal to 1, what is the probability y equal to what is the probability y is equal to I when k equal to 2, what is the probability of y equal to I when k equal to 3, it is this one. Now, we can always write it as a conditional like this. So, this is probability that k equal to 1 and probability of y equal to I given k equal to 1 plus probability of k equal to 2 into probability y equal to I given k equal to 2 plus probability of k equal to 3 into probability y equal to I given k equal to 3. We know these probabilities, these are all 1/3. We have seen that before. Now, what about the probability of y equal to I given that k equal to 1? For that, let us check this Latin square. So, here we see that suppose k equal to 1. So, I know that k equal to 1. Now, let us see if I equal to 1, that is this one. When I have got k equal to 1, then I am fixed to this row, and in this row there is no repetition. So, for any y, any particular value of y, in this case I, it may be 1, 2 or 3, let us say I equal to 1. So, if I take I equal to 1, then y 1 occurs in the first place and the corresponding x this corresponds to the plain text x equal to 1. So, there is only when k equal to 1, y equal to 1 will occur only if x equal to 1. Similarly, y equal to 2 will occur only or I can say if and only if x equal to 2. and similarly for x equal to 3. So, therefore, I can say that probability of y equal to I given k equal to 1 is the probability of either x equal to 1, x equal to 2 or x equal to 3. So, I really do not know which one will it be, but it is exactly one of them, and therefore, whatever be the value of I will have, I can take, since I know that these are equal to 1/3, I can take 1/3 over here and I will get within a bracket probability of k equal to 1 plus probability of y equal to I k equal to 2 plus probability of y equal to I given k equal to 3. What I claim here that this sum will be same for all values of I. So, we have only 3 values of I. What I will ask you is to do on your own and check that if you put y equal to 1, if you put y equal to 1, probability that y equal to 1 given k equal to 1 is probability that x equal to 1, probability of y equal to 1 given k equal to 2, y equal to 1 given k equal to 2 is going to be y equal to 1 given k equal to 2 is going to be x2, probability that x equal to 2, and probability of y equal to 1 given k equal to 3 is going to be probability x equal to 3. Similarly, if you put probability of y equal to 2 k equal to 1, y equal to 2 k equal to 1, x equal to 2, y equal to 2 k given k equal to 2, y equal to 2 given k equal to 2, x equal to 3, y equal to 2 given k equal to 3 is x equal to 1. So, you will have permutations of these 3 probabilities. Therefore, I can write this as 1/3 probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3, and we know that whatever be the distribution of the plain text, this sum of all the probabilities is going to be 1, and therefore, is going to be 1/3. This is what we have in our slide, and then we have a question that what is the probability of x equal to I given y equal to j. So, let us look at that. Probability of x equal to I given y equal to j is equal to probability of x equal to I and y equal to j divided by probability of y equal to j, which is equal to probability of x equal to I and probability of y equal to j given x equal to I. Now, this is equal to probability of x equal to I and this sum, that is the sum over all k's for which I is transferred to j, and here we will see that given any pair of I j, you have got a unique k for which transfers I to j. That is clear from this table, and therefore, I will replace it by 1/3, and therefore, I have got probability of x equal to I, and thus I have got whatever be the values of I and j, probability of x equal to I given y equal to j is equal to probability of x equal to I. We end our lecture by another problem in the same direction, and this is a modification of the problem that I have done just now. Here also we have got the same Latin square, and we have the same we have the same plain text, ciphertext and key space, but we have got and the encryption rule EI is also same we have written here, but there is a little difference from the last example. Here we have a different probability distribution of the keys. So, I have got probability of k equal to 1, probability of k equal to 2 and probability of k equal to 3, they are different. Probability of k equal to 1 and probability of k equal to 2 are equal and is equal to 1/4, and probability of k equal to 3 is 1/2, and you can check that it will all sum up to give me 1, and we are assuming another plain text distribution, that is probability of x equal to 1 equal to probability of x equal to 2 is 1/8 and probability of k equal to 3 is 3/4. Again please see that if you sum up you are going to get 1. Now the question is, does this crypto system achieve perfect secrecy? And the answer is no, but we will see why no. Now we again start from the same point. We would like to know the distribution of the ciphertext. So probability of y equal to 1, it is a sum. Now let us see why it should be whatever I have written. Probability of y equal to 1, and that is equal to probability of k equal to 1 and y equal to 1 plus probability of k equal to 1 and k equal to 2 and y equal to 1 and probability of k equal to 3 and y equal to 1. Now this means that this is probability of k equal to 1 and probability of y equal to 1 given k equal to 1. This is equal to probability of k equal to 2 and probability of y equal to 1 given k equal to 2, and lastly it is probability of k equal to 3 given and into probability of y equal to 1 given k equal to 3. As you have this step, we are not yet in the place where we have come to after y equal to probability of y equal to 1 in the slide. We are in somewhat intermediate step. The next step is to analyze this conditional. I am asking a question that suppose I know that k is equal to 1, what is the probability of getting y equal to 1? If k equal to 1, that means I am over here, y equal to 1 will occur if x equal to 1, and it will occur only once. It is x equal to 1 then k equal. So this probability is same as getting probability of x equal to 1. So I will replace this as probability of x equal to 1 . Then here we have got probability of k equal to 2 and probability, okay, here I have been told that k is equal to 2 and I am asking a question, what is the probability of getting y equal to 1? If k equal to 2, I am in the second row and y equal to 1 occurs only once because it is a Latin square and it occurs in the second column, so corresponding to x equal to 2. So the probability that you will get y equal to 1 given that x equal to 2 is same as the probability of getting x equal to 2. So therefore here I will write therefore I will write here x equal to 2, and in the similar way I have got probability of k equal to 3, and here I will write probability of x equal to 3, and therefore I have to sum up, and now it is not so nice that everything is same. So here we see this is what we have been doing, and if you are careful and take the products properly, here we have k equal to 1, k equal to 2, 1/4 and all that. So, if you do them properly, then you will see that you are getting 7/16. So, this whole thing turns out to be 7/16, because let us see, k equal to 1 is 1/4, x equal to 1 is 1/8 plus k equal to 2 is 1/4 and x equal to 2 is 1/8 plus k equal to 3 is 3/4 and x equal to 3 is 1/2. We have to add it. If we add it, we should get 7/16, and now we have to do the inversion. I mean, we have to use Bayes theorem. So, see, we would like to know what is the probability of x equal to 1 given that y equal to 1. For that, in the denominator we write probability of y equal to 1, which we have already computed. In the numerator we will be writing probability of x equal to 1 into probability of y equal to 1 given x equal to 1. This is something that we have already, no, we have not seen this, given x equal to 1. So, here in the denominator I will put 7/16, in the numerator I will put 1/8 instead of probability of x equal to 1 and this one. So, now again I ask a question that I have got x equal to 1, given x equal to 1, I know x equal to 1 has occurred, that means here. Now, what is the probability that y equal to 1? Now, when you have x equal to 1, y equal to 1 will occur only in one place, and that is when key k1 is chosen, and the probability of choosing k1 is 1/4. Therefore, I will replace this conditional by 1/4 and I will have this, and this gives me 1/7, and please see that this is not equal to probability of x equal to 1, which is 1/8. So, this is what I wanted to say. Thus, we have seen that if I fix y equal to 1, then probability that x will be equal to 1 is it is different. There is a small error over here. This is going to be 1/14. The probability of x given y x equal to 1 given y equal to 1 is going to be 1/14, which is not equal to probability of x equal to 1, and therefore, the crypto system under consideration does not achieve perfect secrecy. I will put many problems like this in the assignments for exercise, and I will welcome your comments and your questions in the discussion forum. So, this is the end of the first week lectures. Thank you.